So we're in probability, right? And probability is a field unto itself. And but the byproduct of probability is actually statistics. But the theory behind statistics is in probability theory. Oh. Okay, apparently I hadn't added on 4.4, so I have it for your enjoyment. And actually, I made that a copy, didn't I? I don't want that to be a copy. It's 4.4. Is it it's assigned. Forget the word copy there. Doesn't matter. Okay, and now if there's no questions on chapter 3, we'll just continue on with chapter 4. I think we went over chapter 1, but let's take a look at the book. Oh, wait, that's a different one, isn't it? All right, textbook. So let's start with 4.2 then, or let's take a quick look. Okay, and that starts on page 131. What happened? Oh, let's talk about properties of probability. Okay. Now, first, you know that we have this thing here, this gigantic collection of outcomes, different outcomes in whatever field we're interested in, and the total maximum of these outcomes is capital N, because this is what we don't know about some particular question about the population. Now, the word population is misleading because you're thinking about people, but it could be anything that and we usually don't know it. And the number of little things here is capital N. And we have this is called and mathematicians can call it like a population space, or population. We call it a space. Is the total collection of possible outcomes in whatever at that instant in time. Okay. And what do we estimate? We take a smaller one, right? And we have a sample. This is our sample space, and it's made up of, little observations too, that are a subset of what we surveyed over here. Does that make sense? And so the whole possible collection of everything in our particular sample is called a sample space. Okay. Now, a subset of them, any subset of this, could be called an event. An event would be a set of outcomes, whatever you're looking for, right? So, and the way we do that, I can call this sub-event, like, let's say A, and if I ask about the probability of that happening, I'm asking what is the probability of the random variable A. Okay, in this case, you could use, like, for example, remember we were doing relative frequency? You could say, oh, well, this event has 2 over little n. Because guess what? How many elements do I have? Little n, not capital N. So with that, now we can start talking about probabilities. And when we talk about, we have these types of, we have complements, conditional probability, Bayesian theorem. Bayesian theorem is very advanced, actually. It has a mechanism by which you can use your experience to put into the equation. It's kind of neat because they're assuming that maybe, given the certain kind of experiment, you have certain years of experience that you can bring into the forecasting model. Did you hear that? A forecasting. Like that? A forecasting model? Yeah? So you can develop one and then... So if we had another event here, we could have the probability of a different event, B, with some probability depending how many observations were in that subset, right? And more formally, we draw the space usually mostly as a rectangle, and we show that this particular is an event A, in this case is a collection of this. And then we have an event B, okay? So if I look at this in terms of geometry, right, the area of A divided by the area of all the space would be the probability of A, you see. And the area of B would be that now, okay? So here's a difficult concept. It's not, It took me a while to kind of wrap my head around it, but we have this sort of thing. So when we're multiplying probabilities, if you want to know what the probability of A and B is, this means and. So it's the two events happening together. Okay, now if they're independent events, this is a very good term or important term. Independent events. That means that A, whatever outcome B didn't affect A. If they are independent, then this is equal to the probability of A times the probability of B. Okay? And that's what it means. So we have the adding rule and the multiplication rule. Okay? Now, you can see if we want to add them together, so then we have something called the probability of A or B. If this or this happens, right, that would be equal to the probability of A plus the probability of B. That's the addition rule. All right? So if I'm asking one or the other happening, it means, right? Somebody say, yeah? You get it or not? Okay, now, watch this. If I go like this, supposing I now want to find, this is your sample space. And I'm going to have event A like this and event B here such that they overlap. Right? And this has a sample size of little n. All right? So we have to be careful now. If I tell you that I want you to find the probability of A or B, right? You're going to have to add in the probability of whatever A is, which is this area divided by the total area, right? And then you're going to add the probability of B occurring, right? But in this case, because there's an overlap, we have to subtract for the probability of A and B. Because we're adding this twice. Does anybody see that? The intersection is being added twice. I took this event, but it's overlapped here. Okay? And then I take this event and add it again. So this middle term's been added twice. So that's why I'm subtracting it once. And this thing could keep going. I mean, I've seen them like this, you know, where you have your, you know, it gets more and more complicated. You know, where you have A, B, and C events. Now, you have all sorts of interactions that are duplicated, right? You have this that's quadrupled, and then you have this that's doubled. And so that makes out, so it's P of A plus P of B plus P of C minus A and C, probably A, C, minus B and C, then minus all of them, A, B, and C. It gets, you don't have to do it, but it's just say, okay, so this, if this term is 0, okay, if this is 0, we say that the events are mutually exclusive. Oops. Events. All right? Now keep this. Look. If you're just adding the two events together, that means they're not overlapping. That means it would look like this, correct? Now, in this case, do you see A is completely mutually exclusive to B? There's no overlap. So the intersection would be 0, right? What you're proving is that these two events are mutually exclusive. Now don't confuse that with this. If I want to say and I want to see and find out what the probability of A and B is, okay? Now, if it's independent, I mean this event doesn't affect this event, or this event doesn't affect that event. Notice, now we're talking kind of like about time. Suppose I have a deck of cards, right? And I'm going to draw 2 cards, correct? So I draw one card, right? Let's say that's event B. Okay? Now, the question is, what do I do with B? If I take event B, a card, and then I set it down and I draw from the deck again. Do you see there used to be 52 cards in the deck, yes? So the first event of just drawing one would be 1 out of 352, right? Now you have to ask the question, is there replacement or no replacement? It's up to you. I mean, it depends how you construct it, because supposing that you're not replacing it, if you're not replacing it, yes, then that occurrence has affected the next outcome. Why? Because there's one more or less card in the whole deck. So your second drawing has changed. Its probability will be, on 1 divided by 351. I mean, divided by 51. You understand? If I replaced it, okay, and draw again, then that first event didn't affect the second event, yes? If that's the case, then you will find if it's independent, then this is equal to the multiplication rule of P of A times P of B. Okay? Now, what happens when this does affect this? Then we say we have to find the probability of A given, do you see that bar there? That means given that B has occurred. This may not be a independent. It might be dependent because there's no replacement. Does anybody know what I'm talking about? Yeah? No? You do? Well, that's one. So what is this equal to? This is going to be equal to the probability of A and. Well, I should say the probability of A, and I should do it like this. Let me so over here I'm doing okay. So if it's conditional, then you'll have to do like this. You're going to have to find the probability of A and B, and you're going to have to divide by the probability of B. This is in the case of dependent. Welcome to the world of probability. This is independent. So if these two equal to it, it's like a test. If this number comes out as this number, then even though I put conditional, it really was independent. So this one here is independent. And this one right here, this is called mutually exclusive. So I don't want you, when you're doing that addition rule, you're talking about adding up events. And if they don't overlap, no problem. You don't have to subtract the intersection. That's the addition rule of probability. The multiplication rule is you multiply it, but one has to ask is if one of these events affects the other. Then it becomes a dependent thing, right? If you don't return the card, then that event outcome has affected the next draw. You get kind of a feel. It's not too easy. I mean, it's easy enough, but you got to kind of sort it out through your mind. What did it mean? Like I said, a good example, the best example is you're drawing from a deck of cards. You actually affected the whole thing if you don't return that card. Then we say that event affected. So now you'll be going to find out what the true probability is. Given that you're not returning the card, you're using this. And it will not be equal to this. All right, I know it's a little bit. Let's see if we can see some examples, because I know you'll like those. And let's see. Okay, so can I make this? Oops. Okay. All right. Okay, so we're going to talk about the complement. This conditional probability is what I put there. It's the probability of A bar, given that B has affected A. That's what it means to be conditional, because the next draw is dependent on your first draw. This is Bayes' theorem. I'm not sure why they threw it in here, but this is a way of doing hypothesis tests, but you can introduce your expertise, like your gut feeling, like me knows something that most don't because you've been doing it for years and years. You can enter it into this mathematical model. It's a way of introducing your knowledge kind of into the equation. It's in the, we call it Bayesian. And the complement is simply this. The complement is, in the whole space. Okay, now we have a sample space, correct? With some event happening, let's call it A. Now, everything that's not A is A naught. Do you see that? And everything in this red area is part of A naught. Okay, so the fame is that the probability of A is equal to 1, which is 100%, minus the probability of A naught. And sometimes it's easier to find out probability by subtracting the naught than going through all the work to find the probability A, just find out what it's not. Right? It's like if you can find someone who's always wrong, you can make a lot of money. You just do the opposite. So this is sort of that way. I've met people like that. A lot of them are my students now over at the prison. Okay. Now, this is called counting rules. That's called combinatorics. That's a whole field in mathematics, too. It's how many ways can some happen. For example, let's talk real quick about counting. Suppose you have a briefcase, and it has 4 tumblers on there for code. Okay, now, look at this thing, and this can take on, we'll say, any one of 10 digits, right? 0 to 9. And does this outcome affect this one? No, it doesn't really, right? It doesn't, because it doesn't matter what this, unless we say we can't reuse the number. Do you see what I'm saying? But let's assume it can go, each one of these, right, can go from 0 to 9. That's 10 digits. And so's that one, and so's that one, and so's that one. So if they're independent, notice that one doesn't cause the other, right? Then it'll be this, you have, this can be any one of 10 numbers, yes? And this can be any one of 10 numbers, and this can be any one of 10 numbers, right? So the total combination will be 10 raised to the 4th power, which is just 10 with 4 zeros, right? So if you're trying to figure out a briefcase, all you have to try are 10,000 different combinations, and you'll be able to crack it. Now, when they hack codes, there are computers that can go through that combination really fast, and they could crack the code. But by keep sending out, trying it. You know how if you try a password too long, it cuts it off. But they keep coming in as a new request, so they'll figure it out. That's why you see the passwords going like this. So now look at this. So I'm going from 1 to 10. Now, if I keep going like this, supposing that I don't want to reuse the number, okay? So now it's different because now they're independent, right? Because this can happen in one of 10 ways, yes? But this can only happen one of 9 ways. And this can only happen one of 8 ways because I'm not allowing you to repeat the numbers once used. Do you see the difference? Now, as you can see here, the order doesn't matter, right? There is no difference from one position to the other. Consider these jobs. And you're all 4 managers, right, of equal pay and power. This is how many ways you can fill it up. Let's say this is how many combinations, right? On this one here, what we're going to end up doing is multiplying 10 times 9 times 8 times 7. And that's how many combinations. Which number do you think is going to be bigger? 10 to the 4 or 10 times 9 times 8 times 7? 10 to the 4th, right? It's 10 times 10 times 10 times 10. Clearly, this one here. Okay, now, if this space is like for a president, manager, secretary, treasurer, now it's different because these are restricted. So once you selected one of your candidates, you can't refill them out. Here, you got to go for another one. You see the difference? So these are classic combinatorics. And there's an equation that I'm going to touch you on. It revolves this thing. I'm not sure if any of you have seen this symbol other than when you're writing a paper. Yeah. You know this symbol, anybody other than him? This is called a factorial. Okay, so if I give you this, 5 factorial, what that means exactly, it's equal to 5 times 4 times 3 times 2 times 1. That's what a factorial means. And they get big fast, because if you go 20 factorial, then you have to multiply 20 times 19 times 18. These are, don't worry if right now, I'm just throwing it out there and then we'll see how it fits in, right? This is part of the counting rules. Counting rules help us count out the combination of events that can happen in our sample space. So let's go on. Okay. There should be a little switch on here where I can just... okay. We're on our way. All right. Okay, so... So the probability of 75 or more girls is 3 in 10,000. 10 million. That's why it's really small to get probability of 75 or more girls out of 100 births. And then B. Okay, so there's such a small thing that they're saying statistically reject the explanations. I wanted to show you the counting rules. So you would kind of expect, right, that boys and girls are born with the probability of how much you think. What's your chances of being a girl when you're born? It seems like it would be 50-50, right? You would think. But it's kind of freaky because in nature seems to know, and for some reason there are 51% boys to 49% girls. Why? Because by the age of 3, the boys have killed themselves out. A certain amount of boys, they're suicidal. I don't know how I made it. But so at the end of 3 years, it actually balances out 50-50. Mother Nature seems to know. So it builds in a few more suicide cases that won't affect the total population. Isn't that cheerful? Okay. So there's the event. You're asking about simple event, right? So you got the event, and then a simple event is one outcome only, not a group of outcomes. That's all. The sample space are all possible combinations of little n. Little n. Does anybody know what I'm talking about when I say little n? Okay, so let's see what's next. Okay. This is an example. Example of event. One girl. This is the possible outcomes. Boy, girl. Here's 3 births. Yes? 3 births. Well, we could have boy, boy, boy. We could have... What, do you believe that is having a girl as a baby affect the next baby? So we could say that these are independent events, couldn't we? Unless you can find there's some way, I don't know, that a baby could affect the next one coming. There's internecine. I don't know if you know that word, internecine. You do? It's it has to do with babies in the stomach cannibalizing each other, eating each other until one survives, like sharks. They actually eat each other until the biggest one lives. So I would say in that case, the other could affect the womb, but you understand? It could be a dependent event. Okay, so guess what? This here, the total count is your n. 1, 2, 3, 4, 5, 6, 7, 8. You see that? So we need counting rules because sometimes these things that count out all the combinations get large fast. Right? Because we've only gone out to 3 births, right? What do you think if we went to 4 births? What do you think is going to happen here? Look at here when it was 1, boy or girl. And here, and if I do one more, right, So if I do the 4 bursts, I don't know if I got this in here. You know, four bursts. Well, let's see. So they're independent events, right? So we got to think. Well, wait a minute. Boys can be, you know, boy, boy, boy. Yes, boy, 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 girl. Now notice that this event. Now I'm going to just move it down like this. Look, boy, boy, girl, boy. This is different than this because the girl came in 3rd and came in 4th there. It's another outcome, right? It's not being double counted, is what I'm saying. And, well, how many different examples? Well, we had 8 here, right? Sorry, eight of them here. Okay. So that had 2, right? To the 3rd power is 8, right? So this would be probably 2 to the 4th power. There are 16 of them. That's your sample size. Those are all the total combinations. So I have to teach you how to be able to, because, you know, sometimes you just can't sit down there and write them all out. They're a huge list. Okay. Any questions? It's still too easy? Okay. I'll press forward then. Okay, so now we're talking about these are events. You see? Event A, event B, event C. And the question that should be starting to cross your mind is now, are these events independent? Are these events mutually exclusive? Right? When I'm talking about mutually exclusive, I'm talking about the addition rule. Okay, so the addition rule really answers the question whether there's an intersection between the 2 events, right? But the idea of whether one event causes another, that's the concept of independence. I want to try to get across the difference between, so let me write it here. So if I have this, if the probability of A or B is equal to the probability of A plus the probability of B, then that's an indication and that's it, and that's what it's equal to. Then these things are mutually exclusive. Mutually exclusive, okay? Now, if they're overlapping, then they're not mutually exclusive. Mutually exclusive not, right, would be this thing with a bar over it. Then you have to say the probability of A or B is equal to the probability of A plus the probability of B minus the probability of their intersection of A and B. In this case, they are not mutually exclusive, and you have to subtract the intersection, right? But when this is the addition rule under probability. The multiplication rule is asking about if P of A and P of B is equal to P of A times P of B. Yes? If that's what it equals to, then we call this thing independent. If this event might affect that event, then you have to use a conditional probability. Remember the word conditional? A given B has occurred, and it has affected A. In that case, that's going to be equal to the probability of finding out what the intersection of A and B is divided by the probability of B. I know it still looks abstract, but little by little it'll start coming into focus. So, the probability of A occurring is the number of times A occurred in the sample space divided by the number of times the procedure was repeated, if it's that kind of procedure. Okay. Let's go next. Dang it. Okay, little n divided into how many events happen in event A, how many occurrences? Subjective probability. Now, where might we get these probabilities from? Do you remember our histogram, our relative frequency histogram? There's a way of getting an approximation to the probabilities, right? Because you use your sample and you saw what bins they fell in. Yes? And if you take the total number that fell in a particular bin and divide it by n, you're going to have a probability calculated from your relative frequency approach. You know, because we know that the histogram that we're using is to predict the actual distribution in the population. Does anybody know what I'm talking about? Does anybody else? Oh, good. I'm not sure. Okay, so here's that brings the idea. If you guys play Lotto, you can like I haven't played it, so I don't know. I mean, I don't know how many numbers do you have to pick. Does any play the Lotto? Nobody? Usually, if you find $1 on the street, they go buy a ticket. But I don't know how many are. But let's say you have to draw 6 for the sake of example. Yeah, six numbers. I don't know what they are. But are these numbers reused, or are they used only once? Right? Somebody let me know. When you're picking numbers, they're not. Are they? Can you say like 1 1 1 1 1 1 1? Does it make sense? I don't think you can. So let's say now you can pick a number, right? If you're picking just numbers right now, they have 2 digits numbers, don't they? So I don't know how far they go. Let's say they go up to 50 numbers. I don't know. So guess what? This would be what? 50 possible ways. Yeah, 49 because we're not repeating it, that particular number. Times 48 times 47 times 46 times 45 times 44, right? So if you multiply together, that would be a sample size of my Lotto. I don't know. In other words, that's how many, that's n. So we can look at that and say there's this thing called a permutation. Okay, and it's written like this. So we have n, a little n, right? And we're going to do permute x of them. So in this case, we're going to have 50 permute. Well, how many spots do I have? 6, right? Okay, I know it looks weird, but let me tell you right here that the permutation of n and choose x of them is equal to n factorial divided by n minus x factorial. Okay, so in this case, we had 50 permute 6. Yeah? So we have how many left? So if I take n minus x, okay? So here I'm going to have, I know what n is, right? It's 50 factorial. Do you agree? That's n, little n, yes? Somebody say yeah. How about n minus x? What is that? That's not hard, n minus x. This is x, that's x. Uh, 44 fact. Okay, let's see. So 50, 48, 47, 46, 45. Okay, so this is 44 factorial. Okay, so what does 50 factorial mean? 50 factorial means 50 times 49 times 48 times 47 times 46 times 45 times 44 times 43. This is a gigantic number. And it's going to go way down here to just keep multiplying till you get, down to the 2 times 1, right? If you have this on your calculator, you can put 50 factorial. Some of you will see a button that looks like this, and then it has like an exclamation mark. That's the factorial function. So now, if I divide it by this, look what happens here. It makes it a lot easier. Because this I'm dividing by 44 factorial, right? Well, 44 starts from here, right? 43, 42, 2, 1. You see what's going to happen? Yeah. So I think this one here, this was not correct because this I just did 6. Okay? And guess what this is equal to? It's equal exactly to what's left. This. So a permutation is when you're not reusing it. Okay. So you'll get used to it. Now we have one that's called a combination. It's called n choose x. And this is called a combination. Don't let it freak you out. I'll give you it's not that big a deal. I'll give you examples of it. It's new, probably. You've never seen it before, I think. So instead of putting a p in the middle, they make this kind of parentheses, and this means n factorial divided by n minus x factorial, which it looks a lot like this, right? But then we further divide it by x factorial. They're excited letters, see? N is very excited. And so if I was going to do the same problem, right, where I'm going to have, 50? And I'm going to choose how many? 6. Right? I'm going to write on top of this car. So I don't know what would look there. Not red. Okay, so that's going to be equal to 50 factorial divided by, well, we already know that this is 44 factorial, yes? Because we subtracted, remember? Somebody say they remember that. Okay, but we're going to, in addition, divide by 6 factorial. Now, which you think is going to be a bigger number? Permutation. This is called a permutation. This is a permutation, and this is a combination. All right, so those are the two equations for permutations, commutation. Why do we do that? It helps us calculate our sample size because it's just too much to count anymore. Even our sample is large, right? I mean, it gets large. Did anybody do 50 factorial? What'd you get? 11 million? Okay, well, I meant on a permutation would be this, right? And then what number was that? 11 million something? I don't know. Something. Okay, well, anyway, okay, divide that into 1. That's your chance of getting the winning ticket, right? On the other hand, if you buy this many tickets, you'll be okay. You'll win. But you got to buy 11 million. And believe me, there have been people, a group got together in Canada, figured out what they did, and they went in and literally bought all the tickets. Now, what determines the payoff? Suppose you buy 11 million tickets. You have $11 million. And you go, I'm going to play the lottery now. But now I got to get it, so I want to get every single combination. I know I'll hit it. Okay? But here's the problem. If anybody else hits it, then the payoff divides by 2. If you happen to put 11 million and 3 people hit it, that's risk. You understand? But you're guaranteed to win. So, I don't know. It kind of depends how willing you are to take the risk. People have tried it. Now, this is also a reason that if you decide to buy one of these tickets, and I don't know if you decide to take the dummy risk, you're more likely to get hit by lightning. You're more likely to be eaten by a shark unless you're not in the water. So anyway, the lottery is considered by economists as a poor man's tax. It's a way of getting tax money out of poor people because overwhelmingly people with low income are the ones that are paying the lottery. And it used to be that it was set up so that the money's coming in was supposed to go to education, right? But what happens is a lot of that money goes into a general fund, and then when it comes time to spend the money, sometimes they draw on that general funds. Or what happens is that a big football team comes to town and says, we want the city to put up an arena and put a bond up so we can place that arena, right? So what happens, in essence, the lottery is going to fund this arena for these rich people, right, at the expense from the general funds. So it really less ends up going to actually where it was supposed to go. Yeah? Just want to cheer you up. And now, so we got that one anyway. Let's go on. It's hard to cover all the material. Okay, you can read that. That's about rounding. How to round. I don't want to do that. Okay, now this is one of the most important parts of probability. It's called the large number, law of large numbers. This is like the crux of all insurance companies. If you own an insurance company and you want to minimize your risk, you want as big amount of and sample size as you can get. You want many members as you can get, right? Let me tell you what happened. Let's say the Affordable Care Act, all right, was made everybody get insurance, right, one way or the other. With that act, you cannot be rejected for a pre-existing condition, which is nobody in the rest of the world can understand how we could even, how it is that we're fighting ourselves not to have it. In Europe or in Japan or many other civilized things, they got national health care, and they just can't fathom how it is that you don't cover, your sick citizens. They don't understand that we can actually file bankruptcy in this country because we fell ill. And we can lose, our wealth. You start working, right, and you get sick too long, you're garbage. They're just passed. Over there, they got completely different side. They're very highly taxed, yes, but they have an extremely good social net, right? I know a lady there from Denmark. Her daughter is 19, got cancer. First thing that the government did is put something in the neighborhood of $200,000 into the mom's account so that she could take a year off to help take care of her daughter. All right, maternity leave in Hungary, when you take maternity paid leave, is for 3 to 5 years, because that kid you're bringing up is a responsibility for the whole country. So it's different. Their mentality is different. The countries there are money back to the people. Here, most of the money goes back to the military industry. That's a few owners. So we get taxed, but then it gets spent in Iraq, and right? So here's what happened, and here's what Trump has done to help gut out this Affordable Care Act. What he's done is he's offered a pseudo-insurance company for healthy people, which does have a pre-existing condition, which has a cap on how much they'll spend, but it's very cheap to get, relatively speaking. You understand? So they're attacking this large number on the Affordable Care Act because what they're trying to do is pull out the healthy people out of the pool for private business, making the premiums go up. Because you're going to have higher risk, you have a disbalance in your sample size. Okay? So, what's the other tendency? The other tendency is that law of large numbers, if that's not, I can show it to you with just flipping a coin. It is possible that when I grab a coin and I flip it 5 times that I get 5 heads. The law of large numbers says as you keep flipping that coin on and on and on, that probability will converge to 1/2. Do you understand? You've had to done enough experiments for it to finally converge to what we expect it to have been, was if it's a fair coin, we expect it to come up 50-50. Is that right? So, this is the law of large numbers, and it was developed by the Dutch are the ones that started the first insurance company. And, for not only can you study trends and make predictions, but the bigger the sample size, you are in effect minimizing your risk, right? Because there's healthy people that pay into the system. So now they're trying to pull that piece off, you see? It's sneaky. But it has to do with the law of large numbers, and that's what it has to do, particularly in the insurance business. So this thing, the law of large numbers, see, it over a large number of trials, a few of them You could say, hey, this coin's not fair. I got heads 5 times in a row. It's just, but you can't tell that way. It's too soon. It's not big enough. Let's see if we can get here. Okay. So, in a recent, there are 3 million skydivers. You can't get me to jump out of a plane. I don't do it. I know it's supposed to be cool and everything, but I just, when you open the door to the plane, I have no interest in jumping out. It doesn't appeal to me, especially, I kind of like my back. When you land, it's like... Anyway, there's that, and then how many have died last year or whatever? There. 21. What's your chance of, they say then, what's your probability of dying? You might risk it, right? I mean, risk is a personal meaning. What is risky for you, right? Suppose that I have, I want to play Russian roulette with a pistol, right? I'm probably not going to do it because there's 6 spaces in there and one of them's got a bullet, right? I don't know what kind of prize you're going to have to answer me for me to do that because I like myself. Okay, so, but what happens if I say, okay, there's $1 million payoff and now you give me a 100-barrel gun? So I know I got 1 bullet and 100. Would you do it then? Well, I still like myself, right? This thing going like that. What's the chances? 1 in 100. But if it's a matter of pulling a trigger in my head, all of a sudden I don't like those odds still. I want better. I want 1 million barrels, right? And then maybe I'll take the chance because what's 1 in a million, see? So what is your risk? It's a very personal kind of... It kind of depends too. Like I find myself as you get older, you start changing your risk equation. When you're young, really young, you feel like maybe you're invincible. That's one reason why insurance is higher for younger people, right? Because they really think they're gods at that age. And they kill themselves, right? There's 6,000 pedestrians were ran over this year. That's pedestrians, 6,000. That's what's in the prison. It's about 6,000. Is it 6,000 being ran over? I don't know. That's one every so many hours. That's not counting, deaths on car accidents. Not car accidents. I'm talking about hitting a pedestrian. And it's gone up. I'm not sure if they think that one reason why it might have gone up is because the use of these cell phones, smartphones and stuff, people are like just walking in front of traffic. I've seen it. I've seen one on YouTube. This lady just doesn't even look at the traffic, got hit. Flew like a football when that thing got hit. I mean, it was like the weight difference and the speed difference between the car and the girl with her phone. She flew like, I shouldn't laugh, but it was like, man. Anyhow. Okay. Okay, here's back to the counting rules. Yeah, how many we have? 3 choices. I mean 2 choices, but look at the different combinations. So if boys and girls are equally likely, so it's imposing that, then those events are equally likely, assuming that boys and girls are equally likely. So look, it says in reality the probability of boys is 0.512 to 0.5. Somebody tell me, how does nature know that? How do they know that a kid is going to try to plug a wire into an outlet? And most likely it's a boy. I don't know if you've been around kids, but there's a difference between boys and girls, I think, in terms of aggressiveness. Like, at least it's been my situation. I had 2 boys, they tore the house up. I mean, like, nothing could tear it. Like, I didn't know it could go that far. But, okay, so 3 children of the same gender. Yes? Well, how many outcomes have the same gender? This is one here, yeah? But here's one. Girl, 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 right? Guess where they got the 2 from? Divided by 814, or 25% chance. Of what? Of 3, of getting all boys or all girls. You didn't know that? Okay. Obviously this, when you have something that's so small, it's extremely improbable. but not impossible. That's why if you have enough stuff bouncing around and jiggling for billions of years, you never know what can happen. Let's see. So they took this here. It says the study of high school, 3,785 texted while driving. There's some more reason there's probably dying while driving. Or a guy who's texting can run somebody over, right? You know what that's called? It's called manslaughter. If it's gross negligent manslaughter, you're going to be one of my students over at the prison. You see? And I'll be talking to you there. But anyhow, that's another reason why people are wrecking, I guess. They've done tests with people that are on the cell phone and drive. They drive like they're really drunk. Your brain does not work. This whole idea of multitasking, they say that the millennials are really good at. No. They've taken empirical evidence and given test results. You're not good at multitasking. You're good at doing things that are just about average because you don't get good at anything. There is a cost to trying to do 4 things at once as opposed to sit down and just go over your math. Okay. So let's go on. I wanted to get to the rules, to the counting rules. Okay, this is a complementary events. That's about as easy as you can get. You have the world broken up into event A and not A. Okay, and so here's an example. Oh, now we got 3 million skydivers, 21 result in death. So if the probability of dying was what? Do you remember 0.00000001? Yes? Guess where this number comes from? 1 minus 0.000001. Yes? Sometimes it's better to calculate the not, or easier. Okay? All right. So, what did I say? I said that the probability...
Isn't that like called like a Fibonacci sequence that's like found in nature a lot too?
Yeah. The Fibonacci is found in a lot of things, including the golden ratio. Am I on yet? Yeah. Okay, so this is just that the probability right here, you can say the probability of something not happening is equal to the 1 minus the probability that it happened. Now, what kind of variable are these? Do you know when we put like A or B? Those are events, right? But when we're asking what is the probability of this to occur, that's what we're asking, right? So the probability of D event not happening is 1 minus it happening. Just as well as, you can do this, which is what happened here. They calculated the chances of dying. So the probability of not dying is 1 minus the probability of dying. Those are your counting. Now we should get into the, okay, these are about odds. I guess you've seen odds. The actual odds of an event is probability of A naught divided by A. Okay, and the actual odds in favor were probably A divided by probability A naught. Look, what's the difference? A naught divided by A is what we call the actual odds against. You're going to see a lot of this in horse racing, gambling. You'll see the odds. The odds are simply the division of the two probabilities. The probability A not divided by the probability A not. This shows the actual odds in favor of winning. Okay? So you see here, 35 to 1. This thing means 2, the double dot. Right? You can also think of it as just a ratio of 35 over 1. Like a ratio of 1 to something else. That's just a little slight variation on probability, because a lot of you, when you go gambling, you hear of odds. It's just the dividing of the probabilities. Okay. This should be fun. This game, this roulette. Oh, I didn't want to do that. This game here, I tried to bust that game. I went to the casino, And you can bid on just color. And if you win, they double your whatever you win, right? And they lose, you lose your bet, yeah? So what we thought we would do is that, if we pick red or black, it's not exactly 50-50, right? Because they have these double zeros, right? But it's close. I'm talking about 50 red or 50 black, okay? So the bet was $2, okay? So you bet $2, and if you lose, you have to bet 4 the next time. And if you lose then, you have to do 8, and you have to double it. So anytime you just keep hitting the color that's not, in order to make up a loss and go forward and actually crack the system, is you have to double your losses and go back to bet, okay? You start to sweat because we got a problem. We got 10 blacks in a row. It can happen because they're independent events. I mean, one roll doesn't affect the next roll, right? So we kept doing that, and I'm thinking, by my calculations, we're going to win, but we have to keep holding our nerves and keep doubling the bet, right? That gets up fast. Well, they got it figured out too. They got mathematicians, so what they do is they stop your maximum bid of like $2,000. So they know that you can rig it to make it work in your favor. We won, but it was sweating kind of. Finally, we got a red. But you could get 100 blacks. Then remember, you're doubling your bet. That's the only way you're going to win. I mean, with a structured event. But then they put a cap on how much you can double your bet. And that makes it all more in favor of the house. Does anybody know what I'm talking about? Okay. The odds are probably the best with obvious blackjack in terms of the casino. And especially if they're using, one deck. By the way, if you decide to buy a lottery ticket someday, you want to play the poor person's tax, what you want to do is you want to bet the high numbers, the ones that are like 30 and up, right? Because they do show a pattern of people who are buying tickets. Most of the numbers that they pick are below 30. So if you place your bet on something that's higher numbered, it doesn't mean you're more likely to win. What it means is you're less likely to have to share it with the next guy. So the payoff will be better. I'm not saying that it's more likely to win, but you won't be sharing it nearly as much as likely. Okay, I don't want that either. We already know that probabilities can't be negative, and it can't be greater than 1. That's just an exercise, so we don't want that. Okay, now, here's the rules I was referring to. This is the notation for the addition rule of two events occurring. Yes? The probability of A, now this is OR. Logically, we use the symbol for OR is this upside down kind of like U. We say A or B. And that is going to be equal to the probability of A plus the probability of B, yes? And just in case, minus the probability of, if there's an intersection, A and B. Isn't that pretty? Kind of? I think it's kind of pretty. That the OR, right? If you do it like this, this must mean that the events are mutually exclusive because there's no intersection. That's not independence or dependence. Independence or dependence is when you don't, the first draw and you don't return it. The first draw, that's talk about independence and dependence, right? The law of addition is talking about whether or not there's an intersection and whether or not they're mutually exclusive. Okay? So now, we have here, the probability of A or B happening is equal to the probability of A plus probability minus the probability of the intersection. Okay? So actually it's a test of mutually exclusivity, right? Because if the intersection is 0, obviously they're mutually exclusive events, right? They don't overlap. Does anybody know what I'm talking about? The Venn diagram. The ones where they show the overlapping events? Okay. This is exactly that. So in this sample space, we're asking, is A... I guess maybe I put a battery again, another battery. Life for the high tech. Oh, did it come back on? Okay. So anyway, this is event A. Right? If they're mutually exclusive, it's going to look like this. There's no intersection. So this term would go to 0. But if there's an intersection, then you have to take into account because you would have added it in twice. This area would be added twice. Once when you counted A, event A, yes? And then when you did B again, you've count this overlap twice. That's why you're subtracting it once. Okay. I don't really want, okay, so. Okay, drug testing. What are disjointed events? Guess what it is? It means there's no intersection. Is that right? There's no intersection. That's what that means. Disjoint. That means the two events are not joined. They're disjoint. It's that. See how fast that worked? That was great. It was right there. Boom. Okay. Now, this thing here, okay, that now when I talk about event A or event B, you have to think of it as a variable. When we have this, when you did it, algebra, and I gave you y is equal to 3x plus 1, I know that y equals mx plus b, where this is the y-intercept, yes? And this m in front, this is the variable, the variable. Okay, x is. This guy, right? Anybody know what that's called? Okay, it's called the coefficient, okay? This coefficient I labeled with the letter m. M is the slope of the line. So I can look here and I know that this one's going to have a slope of 3. What is m equal to? It's equal to rise over run. So if it tells me 3, I know that it's 3 over 1. Whoa, what's so funny? I keep seeing like just about ready to laugh. Okay, so what does that mean? That means you're going to run 1 and then go up 3. So the line's going to be steep. And it's going to be positive. If you have a slope of a line and you got somebody who has a future, right? Then if little guy is walking like this and it walks up, to heaven, whatever. Anything that's this way, m is greater than 0. If you don't have a future, then when you hit this spot here, you kind of fall on your butt, so you fall. You're going to hell. So when it goes down like that, then we say the slope is less than 0 or negative. Quick refresher. Okay? Why did I say that? Because when you were in algebra, and I asked you to graph this, although you probably weren't in my class, this, remember, is a variable, yes? We call this independent variable because we decide to pick whatever value of x we want, right? We put it into here, we multiply it by 3, and we get our y. Y is a variable too, but it's dependent. It's dependent on what we put for x. Are you with me? So normally I would have done a little chart like this. Okay? And then one of the things to do is always find the y-intercept, where the line crosses the y-intercept. And that only occurs when y is equal to 0. Then I'll find out where it crosses the x, or if I have x equal to 0. These are good spots to graph. Okay, and then so if I decide to put, let's say, x equal to 0, yes? 3 times 0? What's 3 times 0? Plus 1. Plus 1? Oh, sorry, no wonder this is all backwards. Let me go x and y. That's okay. So when x is equal to 0, this is equal to 1. Yes? Okay, now when y equals to 0, you put 0 in here and solve for x, yes? Okay, now, when I'm talking about probability of an event A happening, right, that is a ratio of how many elements in A yet divided by the total sample. Yes? That gives us a probability, true? Okay, the difference between, this would be like if I wrote this like this, y equals 3a. Okay, it's a variable. The only difference here is that we're not allowed to choose exactly what a is because it's coming from a process that has randomness in it, right? So we call this guy a random variable. It's a bit misleading because if the event itself is truly random, then there's no prediction ability at all. It's random only to the extent that we don't know what the events are going to be, but they're going to come up with a certain probability. There's structure. If there's no structure, then it truly is random. That's what's misleading. It's a random variable, but the event itself is coming from a process that's not totally random. It's coming in some structure in the data, and we're trying to look for that data, that structure, find that pattern to predict in the future. So we're used to picking values of x, right? In this case, when we try to put a table, we have to go to the experiment and see what actually popped up for A and then plug it in. Okay, so A is a random variable which is coming from a process that has a distribution. And the distribution, how do we get an estimate of its distribution? The histogram. Right, the histogram is telling us what the distribution most likely is of the population. Are we done? Man, we're always having so much fun, time flies.